Hi, my name is Catherine Irvin and I'm from George Mason University, and today I will be presenting on estimating causal effect by stratification. This presentation is based on an explanation of Chapter 5.2 in Counterfactuals and Causal Inferences by Stephen Morgan and Christopher Winship. The key terms for this presentation are causal effect and stratification. Causal effect is defined as something that has happened or is happening based on something that has occurred or is occurring. A simple way to remember the meaning of causal effect is B happened because of A, and the outcome of B is strong or weak depending on how much of or how well A worked. Stratification consists of dividing the population into subsets, and then within each strata or subset, an independent sample is selected. An example would be dividing the persons in a town into a strata according to whether they belong to the upper, middle, or lower income groups. An example research question would be if we were interested in the effect of government programs and policies, such as those that subsidize healthcare, and the causal effect on a beneficiary's utilization of healthcare services. However, for this presentation, we will be utilizing the example presented in Chapter 5.2 of Morgan and Winship's Counterfactuals and Causal Inferences. I will simply be enhancing and explaining their example, which is interested in estimating the causal effect of receiving a college degree and what it has on economic success at 40. In this example, our outcome Y is economic success at 40, and D is our observed causal dummy variable receiving a college degree. S is our observed treatment assignment selection variables, which I will discuss later, and I is our individual. Is it expected that the viewer has some knowledge of the individual causal effect of the treatment equation, and knows that when examining causal inference, we first must acknowledge the existence of two potential outcome random variables that are defined over all individuals in the population. Y1 is the potential outcome, or in our case, the economic success in the treatment, and what it has on the college degree for the individual I. Y0 is the potential outcome in the control state, has no college degree for individual I. Because we can never observe the potential outcome under the treatment state for those observed in the control state and vice versa, we can never know the individual level causal effect in the presented equation. Instead, we can only observe values for a variable which is related to the potential outcomes of each individual. In this case, we use the binary variable di, which if equal to 1, would be an individual receives the treatment, and if equal to 0, an individual receives the control. Because it is usually difficult to estimate the individual level causal effects, we instead focus on trying to calculate the aggregated causal effects. Aggregated causal effects are denoted by the capital E. As a result, we then construct the following equations for the average treatment effect of those who take the treatment and those who do not take the treatment. In our example, the economic success at age 40 of those who receive a college degree and those who do not. Unfortunately, two of these average treatment effects cannot be estimated. These two are known as our counterfactual conditional expectations. The first is the average outcome under the control for those in the treatment, and the second is the average outcome under the treatment for those in the control. So what do we do about the counterfactual conditional expectations? Well, when estimating causal effect, two assumptions that support consistent estimation of the average treatment effect include 1. Assumptions about potential outcomes for subsets of the population defined by treatment status, and number 2, assumptions about the treatment assignment selection process in relation to the potential outcomes. These assumptions allow us to develop the following equality assumptions which aid in reducing the number of unknowns in our prior equation. The naive estimator simply puts the difference in the sample means of the observed outcome variable Y for the observed treatment and control groups. This presentation is not going to go into detail about the naive estimator with regards to its formula. how it's calculated, and the typical inconsistencies or biases associated with it in regards to the average treatment effect. Additional information on the topic can be found in Chapter 2 of Counterfactuals and Causal Inferences by Stephen Morgan and Christopher Winship. Remember our question, which is we are interested in estimating the causal effect receiving a college degree has on economic success at 40. Again, our measured outcome, Y, is economic success at 40, and D is our observed dummy causal variable receiving a college degree, and S is our observed treatment assignment selection variables, which we'll discuss in just a moment. For this example, we are going to assume that our sample is infinity, and thus some of our equations are equal to our population for simplicity purposes. As we begin conducting our analysis, we determine that we cannot use the equations in assumption 1 and 2 previously presented to estimate the average treatment effect, because positive selection ensures that those who are observed in the treatment group are more likely to benefit from the treatment than those who are not. Fortunately for us, in our example, those who receive a college degree and those who do not are unlike each other, and the ways in which they differ are captured by a set of observed treatment assignment selection variables that we denote as S. We consider S to be a mixed family background and preparedness for college that accounts for the pattern of self-selection into college, and it's relevant to lifetime economic success. Our literature review, knowledge, and observation of S allow for a perfect three-category stratification of the data, meaning that individuals within groups defined by values on the variables are entirely indistinguishable from each other in all ways except for 1, observed treatment status, and 2, completely random surprises to the potential outcome variables. As a result, we instead use the following assumptions, which will allow us to estimate the average treatment effect, the average treatment effect for the treated, and the average treatment effect for the controls. We begin by first calculating the joint probability of S, our stratified variable, and D, our control treatment, where the probability of group 1, where S equals 1 and D equals 0, or the control, is 0.36, and the probability of group 1, where S equals 1 and D equals 1, or the treatment, is 0.08, and the joint probability is 0.36 plus 0.08, which equals 0.44. And the probability of the control state is equal to the sum of the probabilities of each group, S equals 1, S equals 2, and S equals 3, where D equals 0. In this case, it is 0.36 plus 0.12 plus 0.12, which equals 0.6. Next, we calculate the potential outcomes of those in the treatment and those in the control for each group, S equals 1, S equals 2, and S equals 3. Remember, for simplicity purposes, we made the assumption that our sample was infinite and thus measurements were equal to those of our population. Once we have each potential outcome value for each group in the control and treatment states, we then move on to getting the aggregate. We start with the control, where we divide each group, S1, S2, and S3 probability by the aggregated group probability of the control, which was 0.6. And then we multiply each by their matched potential outcome and then add them up. So for S1 in the control, it would be 0.36 divided by 0.6 multiplied by 2. When repeated for S2 and S3 and added up, the sum of the whole is 4.4, which is the potential outcome under the control state. When repeated for the treatment, the potential outcome under the treatment state is 10.2. Now that we know that 4.4 is the potential outcome under the control state and the potential outcome under the treatment state is 10.2, we subtract 4.4 from 10.2 and get 5.8, which is our naive estimator. Once we have the naive estimator, we can go on to calculating the average treatment effect, the average treatment effect for the treated, and the average treatment effect for the controls. To calculate the average treatment effect for the treated, we subtract the match S group outcome in the control group from the treatment group and multiply it by their respective treatment probability and then sum the whole. In this case, ATT is 3. To calculate the average treatment effect for the controls, we subtract the match S group's outcome in the control group from the treatment group and multiply it by their respective control probability and then sum the whole. In this case, the ATC is 2.4. And finally, to calculate the aggregated average treatment effect, we take ATT of 3 and multiply it by the joint probability of the treatment, 0.4, and add that to the ATC of 2.4, which is multiplied by its joint probability of the treatment, 0.6, and we get an ATE of 2.64. Meaning for our example, the average treatment effect obtaining a college degree has on economic success at 40 is 2.64. I would like to thank you for taking the time to watch my video in regards to estimating causal effect by stratification. Thank you.